For my physics of sport project, I've decided to study the physics behind basketball. To start off, I will be investigating kinematics in basketball. Maximum speed in basketball. If a player steals the ball while on defense and has a fast break where there is no defender between him and the basket, this player will have to run at his maximum speed towards the basket. The player must do this to ensure that he can score a basket before the opposing team is able to chase him down. Maximum speed has been reached once the player has stopped accelerating and is running at his constant maximum speed. Acceleration in basketball. If a player loses the ball while on offense and an opposing player steals the ball, he will go on a fast break running at his maximum speed towards the basket with no defender between him and the basket. The player that lost the ball will have to accelerate to ensure that he is able to catch the player with the ball and steal the ball back. Acceleration occurs when the player is increasing his speed until his speed is greater than the opposing player's maximum speed and is fast enough to catch the other player before he reaches the basket. Projectile motion in basketball. When a player is taking a three-point shot, they must shoot the ball in a projectile motion from behind the three-point line in order to score the 3 points. The ball must be released at a high enough angle to the court to ensure that the projectile motion of the ball goes into the basket and is not blocked by an opposing player. When the ball is released, projectile motion occurs since the ball is not powered by the player anymore and is only under the influence of gravity, with the exception of little air resistance acting against the ball's direction of motion. For my kinematics calculations, I've recorded myself taking a shot in basketball. I've then inputted this video into Logger Pro, which has analyzed video and has given me the total time taken, as well as the distance and speed both vertically and horizontally. For my first calculation, I will be solving for the maximum height of the shot. This is a picture of my solution. This solution includes two unique calculations, and the final answer is 4.2 meters for the maximum height of the shot. For my second calculation, I will be solving for how long it took for the basketball to go into the net. This is a picture of my solutions. This solution includes two unique calculations, and the final answer is it took 1.2 seconds for the basketball to go into the net. Now I will be investigating forces in basketball. Newton's first law. A charging foul takes place in basketball when a dribbler charges into a defender who has already established a stationary position on the court. Newton's first law occurs on the defender as the force of gravity acting down on him and the normal force acting up on him from the court are balanced, providing him a net force of 0. Therefore, the defender is in a state of rest and wants to remain in this state. When the dribbler charges into the defender, he disrupts this state of rest and receives a charging foul. The foul is beneficial for the defending team as they receive the ball or potentially free throws if the offense was in bonus. Newton's second law. When a player takes a shot, the ball is launched in a projectile motion into the hoop. When the ball is in the air, the only force acting on it is the force of gravity with the exception of little air resistance acting against the ball's direction of motion, which is not considered when calculating for the net force. Newton's second law occurs here in the force of gravity. Since the net force is equal to an object's mass multiplied by its acceleration, this can be modified to the force of gravity is equal to the mass of the basketball multiplied by the acceleration due to gravity. The force of gravity occurs when the ball is released as it acts downward on the ball until the ball reaches its maximum height and then pulls it down into the net. The player team is rewarded points for the made shot. Newton's third law. When a player is running up the court to receive an outlet pass, Newton's third law occurs. When the player applies an action force from his foot onto the court applies an equal and opposite reaction force from the court back onto the player's foot. This equal and opposite reaction force propels the player forward. When repeating this action and reaction force more frequently, alternating between both feet, it propels the player into a running motion. This running motion allows the player to get up the court and receive the outlet pass. Force of friction. Whenever a player is running in any direction, kinetic friction occurs. When a player is running, kinetic friction acts the opposite way that the player is running, allowing the player to move but with some resistance. Kinetic friction is not as great of a value as the force applied in the direction of motion is which causes the slight resistance. Without kinetic friction, players would be sliding all over the place as there would be no force acting against their direction of motion. Having a high kinetic friction value is equal to the coefficient of friction between your shoe and the court multiplied by the normal force of your body, which is equal to the force of gravity. This is why having shoes with a high coefficient of friction on the court, high traction, is very important as they resist you from sliding. Whenever a player is running in any direction, we know that the kinetic friction is occurring. For my forces calculations, I recorded myself with the ball in my hand, having my arm at the horizontal, raising it up all the way until the ball rolled off my hand. Then using slow-mo video analysis, I found the exact point at which the ball was just about to begin to move. I then used an online protractor to measure the angle between the horizontal and the point at which my hand and the basketball make contact. I also used my personal scale to measure the mass of the basketball. For my first forces calculation, I've calculated the force of gravity acting on the basketball while it's in the air. This is a picture of my solution, and inside of my solution I've included the free body diagram of the basketball in the air. The final answer is 20 newtons down for the force of gravity. For my second calculation, I've calculated the normal force acting on a stationary ball on the ground. This is a picture of my solution. Inside of my solution, I've included the free body diagram of a stationary ball on the ground. The final answer for the normal force acting on the stationary ball on the ground is 20 newtons up. For my third calculation, I've decided to calculate the coefficient of static friction between a leather basketball and a hand. This is a picture of my solution. Inside my solution, I've included a free body diagram of point just before basketball is about to move on hand. The final answer for the coefficient of static friction between a leather basketball and a hand is 0.70. Now I will be investigating energy in basketball. Work. When a player is being posted up down low in the key, they have to defend by pushing the other player back away from their basket. When the player is pushing back against the opposing player, work is occurring. Since work is equal to the force applied multiplied by the change in distance, we can modify that to the work being done by the defender pushing back against the opposing player is equal to the force he is pushing with multiplied by the distance that the opposing player has moved. If the defender exerts a force pushing his player back, then his work will be positive. However, if the defender exerts a force but the opposing player backs him down further in the paint, then his work value will be negative as the direction of motion is opposing to the direction of his applied force. Whenever a defender is playing post defense, work is always occurring. Positive work is a result of good post defense, and negative work is a result of poor post defense. Power. When a player is being posted up, down low in the key, they have to defend by pushing the other player back away from their basket. We already know that when the player is pushing back against the opposing player, work is occurring. If the offensive player is also pushing back, causing the defender to push for a duration of time, power is now occurring. Since power is equal to work divided by the total time taken, this can be modified to power equals the work at which the defender is pushing divided by the total time he has pushed for. Power is what allows you to do work for a duration of time. Having power will reward you with good defense as you're able to push the opposing player back. Energy conservation. Whenever the ball bounces in basketball, energy conservation is occurring. Notice that when the basketball is dropped, it never returns to the original height it was dropped at. This is because the ball's energy is transferred into other forms, but the total energy will always be the same as it is a closed system. The ball's total energy before it's about to be dropped is equal to just its gravitational potential energy since its speed is 0 meters per second. When the ball is about to make contact with the court, all of its gravitational potential energy has been transferred into kinetic energy. When the ball does make contact with the court, most of the energy is transferred into elastic potential energy. However, since there is friction occurring between the ball and the court, energy is also transferred into sound and heat energy. When the ball bounces back up, all the elastic potential energy is transferred into kinetic energy, which is eventually transferred all back to gravitational potential energy once the ball's speed is 0 meters per second. Since energy was lost to sound and heat, this is why the ball can never return to its original drop height. For my energy calculations, I taped a measuring tape to the wall and recorded myself dropping a basketball and the basketball bouncing to its rebound height. Then, using slow-mo video analysis, I was able to find the total time taken for the ball to hit the ground. Also using slow-mo video analysis, I was able to find the rebound height of the ball. I then found the specific heat capacity of leather from engineeringtoolbox.com. And then again using the mass of the basketball, which I got from my personal scale. For my first calculation, I calculated the speed of the basketball just before it hits the ground. This is a picture of my solution, and the final answer for the speed of the basketball before it hits the ground is 5.4 meters per second. For my second calculation, I calculated how much power the basketball generates. This is a picture of my solution, and the power that the basketball generated was 64 watts. For my third calculation, I calculated for the efficiency of the basketball. This is a picture of my solution, and the final answer for the efficiency of the basketball is 68.7%. For my fourth calculation, I calculated the change in temperature, assuming that all the lost mechanical energy went to heat energy in the basketball. This is a picture of my solution, and the final answer for the change in heat temperature is 3.1 times 10 to the negative 3 degrees Celsius. This is a picture of my first energy transformation diagram, which is of a basketball bouncing to its rebound height. This is a picture of my second energy transformation diagram, which is of shooting a basketball into a net. For my piece of equipment, I will be studying the physics behind an actual basketball. An actual basketball is used for pretty much everything in basketball as it is the most important piece of equipment. It is used for everything from dribbling it, passing it, shooting it, and much more as it is required to go in the net in order to score points. Speed. Speed is related to a basketball when you pass the basketball, as the speed of the basketball increases from 0 meters per second until it reaches the player you're passing the ball to. The speed of the basketball when it reaches the receiving player is equal to the total distance the ball has traveled divided by the total time it has taken. Friction is related to a basketball as it feels the force of kinetic friction between a player's hand and the basketball whenever the player is dribbling as the ball is still moving when it's touching the player's hand, which is equal to the coefficient of kinetic friction between the player's hand and the ball multiplied by the normal force acting on the ball. The basketball also experiences air resistance while it's being shot or passed as it is moving through the air. Forces. Forces is related to basketball as it feels the force of gravity acting down on it when the ball is being shot or passed, which is equal to the ball's mass multiplied by the acceleration due to gravity. Whenever the basketball is on the ground, it also is experiencing a normal force acting upon the ball, which is equal to the force of gravity. The basketball also experiences many applied forces whenever a player moves the ball in any direction, whether they are shooting, dribbling, or passing it. Energy conservation. Energy conservation is related to a basketball when the ball is being dribbled, as the ball's energy is in the form of kinetic energy when the player is pushing the ball down to the court with a bit of heat energy lost due to friction. It then transfers into elastic potential energy when the ball hits the ground with some energy lost due to sound and heat because of friction. The energy then transfers back into kinetic energy when the ball is moving back up to the player's hand with some heat energy lost again due to friction. Then the energy transfers into elastic potential energy when it hits the player's hand with some energy lost due to sound and heat because of friction. This continues in a cycle as the player is dribbling the ball. These are pictures of my references for my project. Thank you so much for taking the time to watch my physics behind basketball project.